Okay, so I guess today we basically already have enough in place so that I can kind of like show you how everything starts fitting together. Just to kind of like remind you a little bit of what we were doing last time. Let's see if I can start there maybe. Here we go. Okay, so the idea, as I was telling you, is that uh, we have two matrices A and B, and the condition that we are interested in working with is that their product is a zero matrix. Okay. Now, the reason why you want to say that their product is a zero matrix is that what that tells you is that essentially you have like this kind of like situation in the middle where like if you look at the null space of the matrix A, then because once A times B equals zero, that means the column space of the matrix B lives inside the null space of A. And again, like the column space is just another, instead of the column space, you can call that the range of B or the image of B. Like, there are many different ways for referring to that, but I'm just, I think, using kind of like the standard terminology from linear algebra so that it's more familiar. And so once you have a vector space living inside another, right? The idea is that you could establish this equivalence relation where you're saying that two vectors are related, two vectors in the null space are related, right? If their difference happens to land inside the column space. And again, that is something that's useful to try to do once you know that one vector is a subspace of the other. Okay. And then what we were focusing on last time is that the equivalence classes for that, you know, usually you call that the quotient of two vector spaces. But there's like a more concrete way for us to work with this, which is not as abstract. And so that's what I was explaining last time, because essentially, again, just to summarize what we were doing, if you look at essentially like you can look at the part inside the null space that also belongs to the orthogonal complement to the null space, to the that also belongs to the orthogonal complement of the column space of B, which is kind of like this region that I colored here in pink. And again, like it's something we have been working on with before when we were talking about this equivalence class. But essentially, you can think of that quotient as being represented by the vectors that live in this intersection. So after a lot of things, essentially what I'm saying is that we can just focus on the intersection of these two vector spaces. So you have two matrices A and B, and you look at the null space of A and intersect that with the null space of the transpose of B. And that's kind of like the space that we're going to be working with. Okay. Now, what's even better, which is what I was telling you last time, is that here you're thinking of this as the intersection of two vector spaces, but that it is possible to combine that to represent that as just a single null space. But for that, you have to introduce an extra matrix. Okay, so that's kind of like the matrix that will be appearing often in our class. So it's this matrix that I was calling last time the Laplacian matrix. Um, and it's called the Laplacian matrix because literally in calculus it would correspond to the Laplace operator. If you go through the details, I might put something about that for the next assignment because it's useful to see that connection. Just because the Laplacian is like a useful thing, but whatever it that is, like a name, you can kind of ignore it. Doesn't matter too much. But the way this matrix is built is just like you do A transpose A plus B transpose. And the reason for that particular choice was that if you look at this diagram, it is that if you do the operation in this order, that's kind of like the two ways that you can kind of like go back to where you started. If you start with the vector on Rn, which was kind of like the middle vector space that we had, because remember, like we had three vector spaces and Rn was one in the middle. So with the two matrices A and B, if you want to go from Rn to Rn, like you can, like, do it two different ways, which is like this two that I'm showing you there, and that you can like add up the two both possibility, and that is what we're calling the Laplace matrix. Okay? And then the idea was that this matrix has some interesting properties, which is what I was trying to show you last time. Like, for example, it's symmetric. It's a symmetric matrix. Well, also it's squared. If it's going to be symmetric, it's definitely can only happen if it's squared. And its eigenvalues are non-negative, which is kind of like an important fact, which we'll talk about that when we talk about graph theory, because it's an important matrix for a graph. Um, and then the last thing that I was telling you about, where I got a little bit stuck during the last 5 minutes, is that yeah, you can show that the intersection of these two null spaces is just like the null space of the matrix F. So the proof actually wasn't too bad. I just like if you don't even really need to use that A times V equals 0. I just thought like like usually this matrix is defined only in that context. But if you essentially like you can read it, but it all boils down to wait, we did it right here. Well, it all boils down that if you had a vector that is in the null space of the matrix, right? The matrix, if a vector is in the null space of the matrix, then the matrix times that vector has to be the zero vector. So you take that product with the vector q on both sides of the equation, and that still gives you the zero. The number. Well, now before it was the zero vector, maybe I should put like an arrow to not make it too misleading. This is like on the previous notes, by the way, so it's already on canvas. But and then once you have it that way, you can kind of like use like the magic property of the transpose, which I mentioned before, where you know the point of the transpose is that you can kind of like move it to the other factor when you have a dot product. And so if you play a little bit with that, you just end up finding this equation in blue. And the only way for the sum of two norms or two lengths to be zero is that each of them individually is zero. That allows you to conclude that A times U equals zero and B transpose times U is zero. And that's what it means to be in both null spaces. So in fact, you don't need that A times B equals zero, which is nice to know. But usually this is only used in the context where that happens. Outside of that, I don't think there's like much of a use for this matrix that I can think of. So usually you're interested in that case. But yeah, this matrix is going to become like well, not that we're going like if we do computations, it would be on the computer, But this is the only matrix for which we're going to be finding things off, basically. Like so, everything will be the null space of this matrix, null space of this matrix, null space of this matrix. It's just that it will be under many different circumstances where we compute this matrix, but it is always going to have the same definition. So it's kind of like amazing that it kind of like just gets used over and over and over and over, and that's it. Um, so that's kind of like a summary of where we are. But as I was saying, now we have enough in place to just kind of at least show you a concrete application of how these metrics are, well, concrete by mathematical standards. We'll get later into actual applications, but right now it's more like, oh, how a mathematician will use it, so okay, so making sense. Okay, before I say that, let me mention something that I had maybe said at some point before, but it's a useful idea. So I want to kind of like put it kind of like in more generality. So before we continue, and then I can show you how we're going to use this. So here the useful thing is that, or question, if you have a set, or maybe how can you associate this? Let's write it like this. How can you associate a vector space to a set S? So like here, and especially because we're thinking about the later application for data science, where like like you always deal with a finite number of data sets, right? Like like you could think of them as measurement values or something of that sort. But usually like the list of like even if you have a continuous problem, like you would discretize it so so that you can store like a finite list of values on the computer, even if it's like a ginormous like list of like 10 to the 10, like, well, I don't think you could store that much, but like it could be millions of entries, but still, like it's a finite number. So let's say you have like a finite set, uh, although you can do this in more generality, but let's say you have a finite set, which I'm just going to call S1, S2, S3, up to Sn. So those are like the n elements of this set. So this set has n elements. Right? And again, like sets in they can represent many almost anything. So it's more or less any collection that you could think of. So there could be, it could be a set. The set could represent the names of the students in the university. It could also represent like the first n integers, 1, 2, 3, 4, 5, up to n. Like there are so many different uses for them. But so in particular sets, the way a mathematician would say this is that you don't have a lot of structure. There are not many operations that you can do with sets with the elements of the set. Like, so for example, if the set represents like names of people, like you cannot add names of people, like John plus Mary doesn't really come with any particular meaning. So the elements of a set, there is not much you can do with them if you're thinking about like traditional mathematics operations. So there are not many operations you can do with the actual elements of the set, okay? Because again, the set can be quite abstract, since it can be very abstract. But something you can always do, there's something you can always do, which is to consider functions that are defined on this set that there's real numbers. But which take real values. So for like by that I just mean like imagine that's why this Venn like we're like a place where this Venn diagram notation for sets is kind of convenient. Where like imagine you just kind of like represent the set in this way with this diagram where like you have n elements. Uh, and then you have n elements as your set S, and then you have like the number line, the real line, right? So a function from this set into the real line essentially means like for each of the elements of the set, you have to assign it a value, right? So for example, it could take the first element and give you this number. It could take the second element and give you this other number. There's no like you are allowed to send it to the same number, right? So like you could take this element as 3 and send it to the same one, right? And in general, like like the function just like will map will send any member of the set to some number on the number line without any specific rules that applications of perceiving. Yes, sorry.
So like, let's say you had these elements that multiple like different characteristics that then give you a function that maps to a vector with like, let's say instead of like for a name, you have like first name, middle name, now.
Okay. Well, the thing, right, like, okay, like if you're thinking about the students' names, right, like with first and second name, or first and last name, right? They're like, I mean, they're like, well, if you're thinking about kind of like individuate, like two traits that they have, right? Like in that case, it would make more sense actually to send it to a pair, right, of numbers on R2, right? So it's not going to be No, I was still actually wouldn't think about that as kind of like going to R. I would think about it as being going to R2 because that's kind of like a way to kind of like keep track of those two traits. So here it's not there's going to be a vector, but it's not quite I think the way you're thinking about it, because it's just like like an assignment of a number to each of these elements, right? So like somehow like a better example for in this case would become like the weight, right, of each student because that's something that naturally already comes with a numerical value, right? So like you could assign to each student if the set is kind of like the students in the university, then the weight would be a function, right? That gives you a number. But if you wanted to say, for example, keep track of the weight and the height, right, like then you have to send it to a pair of numbers, right? Like so it would each be going to R2 in that case, right? So here I'm thinking about it more like, oh, there's like actually just like a single trait, right, that I care about that somehow can be assigned a numerical value, maybe in a natural way, other times not so natural, right? Uh, like with the image, or even with these images, right? Like for the pixels, I guess, like when you send it to like this RGB color code scheme, right? Like it's actually three numbers, right? Like so in that it's like that one is actually going to R3, right? So I'm kind of like doing, of course, like what does it mean to go to R3? Like means that you go to R3 times, right? So if you understand how the functions to R, basically by extension, you kind of like know like the more general case, right? But here, like it's more in that sense, it's more just like a single numerical property that we're studying, if you want to think about it that way, if that makes sense. Um, but there is going to be a vector in a moment. But yeah, I'm going to get there almost immediately after I finish drawing this diagram. So mathematicians, so the thing is like, um, the nice thing about thinking about it that way is that you can consider, like there are many different functions like that weight or height, there are two different functions. So you could consider all the functions from this set into the reals. So mathematicians have a name for it, well, there are two ways to write it. Like one is more convenient than the other, but let's see. So just like a little bit of notation. This one, I'll explain why it's written also in this way in a moment, a little bit less clear. The first one is kind of more explicit, like, it's fun for functions, right? And then it means like you're considering all the functions that takes elements of this set, into the reals. So as a set, this is kind of like an element of this set is a function that goes from from the set into the real numbers. Okay. So it's like just like all the possible functions, basically. So this curve represents all possible functions. Is that okay? Does that make sense? What's kind of nice about this set is that this actually, even if the set that you start with, right, as I was saying, this set could just be like, it could just be like list of names or whatever. Like it doesn't have much that you can do with it. But the set of functions, these numerical assignments, they are a vector space always. So this set of functions is actually a vector space. This is a vector space. Why? Because you cannot, if you can have two functions together, you can multiply a function by a real number because they take their real value. So the thing is like the kind of like the cool fact is that regardless of what the set S is, this can always be thought of as a vector space because you can have functions and then you can like multiply functions by a scalar. So this is always a vector space. In fact, it's one that but I'll mention in a moment why it's even more concrete than this. It's always a vector space since you can have functions together. Since you can define the sum of functions. and a function times a scalar, right? And the product of a function times a scalar. And that's all that you need for a vector space, if you think about it. What is a vector space? It's a set where you can define a sum and when you can multiply elements of that set by a number. And that's something that you can definitely do with when you have real valued functions. Okay.
You say the sum of two functions being f of s one plus f of s two, something like that.
Let me, yeah, I'm glad that you point that up. I mean, like, right. I mean, actually, okay, so let me put it like this, you know, you have S1 up to Sn, right? You have the number line. Okay, so I'll use blue for one of the functions, right? So this is the first function, f. So for example, this would be f of s1, and this would be f of Sn, right? If you had a second function, did I call that? Well, I don't think I gave it any names. Let's call the second function g, right? Sorry, it doesn't have to go to the same number. I don't want to go like bias it in this way. So this could be g of s1, and let's say this could be g of Sn, right? So, what would f plus b g? F plus g be, right? What is f plus g? Right, I'm saying like you can add the function. Well, to specify a function from this perspective is the same as just saying what you're going to do to every element of the set, right? So I just have to define what I want this to do to add some element s. So I'm just going to define that as f of s plus g of s. So it's just at the same s, you see. So to say what this is, right? Like this, you need to say what it does to every element of the set. So I think, this may be more of a computer science definition, like, or notation for like when you're defining things. I don't know if they use like the case three horizontal lines or like maybe two dot, like, um, but when you're defining something like sometimes you write it differently. So all I'm saying is that the way I'm defining this, f plus g, I have to say what I mean by f plus g at an element of the set s. So I'm just going to define that as f of s plus g of s. Sorry, and this one should have been in red. I should have used, I'll use red. The idea is that because the output, they are ordinary regular numbers, so that can be added without any controversy, right? And you do know how to add their outputs. So you can define the addition of the functions as just, whatever gives us outputs, like the sum of the corresponding, whatever gives us an output, the sum of the corresponding outputs. Okay. That making sense, man? And kind of like the same would work with multiplying the function by a scalar. You just have to say what it does to every element of the set, and that just multiplies the output by that corresponding scalar, right? Like, so if you had a scalar c, what does c times f mean? Well, again, that you want to think about it as a new function, so you have to specify what you want it to do on on a particular member of the set, and so you just define it as c times f of s. But the idea is kind of like again, kind of like if you think about it in terms of inputs versus outputs, the inputs themselves, they may not have a lot of structure because you may not add names or you may not add like, you don't know how to multiply colors or things like that, right? So the inputs themselves don't have much you can play with, but the outputs, as long as the outputs like are, for example, real numbers, because you can add numbers and things like that, then you can define more properties on the space of functions, which is inherited from the properties that the output space has. The output space just being like the regular real numbers. Okay. Okay, so much. Oh, but here's like a very let's be even more concrete. And maybe like a more discrete math perspective. What does it mean? Okay, if the set is finite, what does it mean to specify what the function does at the elements of the set? You can think of that as a list of numbers, right? So another way to think about, another representation for the function is as a list, right? Because like if you want to say what the function does, you just have to tell me what it does to the first element, what it does to the second element, right? And what it does to the third element. It's kind of like a collection of numbers, but it's ordered, right? It's an ordered collection of numbers because now if we already order the set, if we call this like the first element, the second element, the third element in the set, if you order the outputs, that kind of gives you a way to know which one you were referring to, right? So, knowing what the function does is the same as knowing that these n numbers, right? Like the values for like, that n possible assignment that the function has to give to the n elements of the set, right? That makes sense. But from that perspective, what is this? It's just a vector, right? So from this perspective, a function from a finite set to the reals is just a vector in Rn. So this is the same as a vector in Rn. So this is a vector. And this is something like, for example, the already like if I'll talk about Kirchhoff's laws later, but that is already if you ever like have done that with us for electric circuit, you kind of like already use this idea there because if you think about it, like it's two, I think that's how we just call this. So for example, if you have like an electric circuit, like again, I'm not going to get too much into the details here, but I'll do more interesting applications with those later on. You know, like maybe you have some resistance, or like what a resistance or resist. Oh my God, I totally forgot the terminology for this of these things, but RLC, right? Like so,
Yeah.
and then the C is a capacitance, right?
Doctor and register.
Yeah, okay, what, right?
Unless it's
Whatever, the inductor, right, whatever, but like, yeah, there is like, for example, here, like, let's just say that you thought about this as being built out of like four edges, right, like it has like four edges. And then what is an electric current? It's an assignment of a number to each of these edges, right? So if you thought of this as kind of like, and in fact, this is going to be a useful example for in a moment. But here if you can think of this as having like an edge set, right? So like an edge set. I'll call them E1, E2, E3, E4. Right. Just because I'm thinking about it as being made out of like four sides. Well, if you want, in this like circuit analysis, like, when you represent them, you kind of draw like the electric current passing through the circuit, right? And you kind of like write, I don't know, I1, I2, I3, I4, or whatever, right? But those are just like numbers which would be positive or negative or whatever. But that is just like an assign, again, the edge set by itself is kind of like a set. There's not much you can do with it, but you can assign a number to each of the edges, right? Which represents like the electrical current. So you could write this as like a function I, right? And I guess that's why an electrical engineer would like to use J for negative ones. I don't know if do not mess it up with the I here, but if you have like I don't know if I should do an uppercase or lowercase, but let's just call it I like this, which would be from the edge set into the reals, right? And what is I of an edge? I of an edge is just like the electric current through that edge, passing through that edge, right? Which in principle, I guess it could be positive, negative, or zero, depending on how, like the current's interpreted, and all this stuff, like, moving one direction or the other. So it can be like any like principle, like I suppose, like any real number. So the electric current. But like again, another way to specify like the currents would just be to kind of like say, well, let me give you, because I'm thinking of this as having four edges, right? You just say, well, let me give you a vector in R4, right? With the first entry is that the current through the first edge, the second entry is the current through the second edge, and so on, right? And so this would be the same as something like, you can even write it like I of E1, I of E2, I of E3, and before. I mean, it's such a natural thing that you don't even think that that's what you're doing, right? Like, but it is like a function from the edge set to the reals, like like what like from this perspective, right? Like what an electric current would be. Uh, and then that you have a vector space, which is a vector space of currents, right? Like because again, like you have it. Well, I guess if it's a linear circuit, right, like where you can just have things, we don't worry too much about like messing it up, like its behavior. But all that I'm saying is that all this it's kind of just like a way of systematizing things that you kind of like already do, but don't put too many names like attached to it, right? Um, so the point is that when you have finite set, thinking of like a finite set with n elements, a function from of that finite set into the reals is the same just as a vector of in Rn. So in fact, Rn is represents so from this perspective, the functions from S into the reals is just Rn itself. Like, so every vector in Rn represents a possible function from this point of view. So every vector in Rn is a possible function. Okay, something consistent. Yes.
This example would be R4 and you have like this specific.
Right, in this case, with because I drew it as having four edges, yeah, I would think about it as being R4, right. In fact, like here's what this is a little bit of an abuse of notation, but it is like a very common thing that you would see. Like, so I'll call this as an abuse of notation, but that is really how we're going to use it in a moment, like in a couple of minutes. I always let's see what is February. Yeah, it's like the time on the internet, but for some reason, like whenever I plug it through cable, it says like what like on January 9th or some weird reason here. But this is definitely not January 9th. So I have to check the time to make sure I'm not going over. Okay, so for as an abuse notation, like so what I was saying is that I could give you a vector, right? So let me just write like a vector, just in this case of R4, because like that way I don't have to write too many things. So like, maybe the vector is 3, -1, 0. Well, actually, I don't want to write 0 so that I can write something, so that I don't have to omit anything. So So this could be my vector in R4. Again, in this interpretation, this would be the current through the first, through the first edge, the current through the second edge, the current through the third one, and the current through the fourth one, right? So another way of writing this, if you want to be more like, to just kind of like emphasize which edge you're talking about, you can write it as you could write this as 3E1 minus E2 plus 2E3 plus 3E4, right? I mean, the point is that, again, the reason why I'm calling this an abusive notation is that this is strictly speaking nothing that has a particular meaning, right? Because again, you cannot like kind of like per se add edges together, right? All that I'm saying is that you kind of like write it more as a linear combination, right? To kind of like because first it's a little bit more simplified way of writing it instead of like having like this kind of vector, but also because like you can just immediately read off, you know, you can just immediately read off the currents as the coefficients in front of each of the symbols for the edges, right? So the reason of doing it this way is that sometimes it feels a little bit like less preferential, because if I write it this way, it kind of like feels like more like order dependent. Like which one are you calling the first edge, which one are you calling the second edge, because that's how the spots of the vector getting filled. Here it's just like, you just have like name for the elements, and then the coefficients in front of those names in the set just represents the value assignment that you have. So a mathematician sometimes calls this like a formal linear combination. Like the word formal means that we don't have a particular physical meaning for it. It's just kind of like as a notational thing, we just write it out in the same way that you would write out like, like the sum of things that you can like actually add, right? Because again, there's not like a meaning like for us like of what it means to add edges in that sense. It's more like, oh, this is just like a proxy to refer to the currents through the edges, like in this Kirchhoff laws case, as an alternative to writing it in this way. It's just like a more elegant way of saying of writing it. So, but it's very common. Like we'll see this when we talk about like I think I should be able to give you an example today about like these matrices, but it's very common to do it this way. So this is going to be a formal called a formal linear combination. And the idea is that the coefficients, like so like in general, like if you had like in the general case, if you had f of s1 as f of s2 up to f of sn, in this like fancy notation, you just write this as the sum from I equals 1 to n of f of si times si, right? But the idea is that you don't, again, you don't kind of like mix things that come from different elements. So you don't try to combine 3h1 minus h2 into a new thing, right? Like that's kind of like left as two separate things, which is actually what happens when if you thought about this as the basis vectors, right? E1, E2, E3, E4, that's kind of what you do, right? If I write like, or in physics, if you have like the vector, if you have in physics like the vector, I don't know, 2i minus 3j plus k, you don't try to merge this into something further, right? You just leave it as 2i minus 3j because these are a basis, right? These are a basis ij and k are available for R3. So from this perspective, what you're thinking is that each of the elements in the finite set kind of like maps or is assigned one of these like standard basis vectors from Rn. So that's why you don't try to kind of like merge them anymore. So kind of like it, so from like, from this perspective, each of the elements of the set is being represented by one of the standard basis vectors in Rn. Of Rn. So if you wanted, you could write this also like as, which would be more true, like f of si times ei, right, where the eis are like the canonical basic vectors, like, with the generalizations of I, j, and k. But but it kind of like, instead, writing it this way is still kind of like reminds you a bit more about what the underlying set was. So that's why it's more useful to, you know, to kind of like keep it this way. Like, in fact, with names of people and the weight example, it's a little bit more clear, right? Because like, like here's another example where like it's less ambiguous what's going on, right? Like if the set had been like, like Alice, Bob, and Charles, right? And the function just gives their weight, right? And f gives their weight. Then something like, if you said something like 150 Alice, right? Well, I guess here, like the weights, let's say like they would always be in the negative, right? But 160 Charles, like the point of what I'm saying here is that you just leave that at, oh, you just read that as, oh, the weight of Alice is 150 pounds or whatever, like what Bob's weight is 176. You don't try to combine that any further, right? And that is the same as this vector in R3, right? And that corresponds to this vector in R3, which is 150, 176, and 160. But okay, so maybe self it's kind of like a detour of what, but it's a useful detour because it's a useful idea to have in mind that you can think of a function of a finite set as a vector. That's not like a very useful idea. The reason why, oh, just to maybe explain this notation, like why is this other notation used like for like the function set? That is because okay, let me just explain the other notation. It's also like a useful thing to know. That if y something like this, when you for like the functions of s into r, the reason for that is when the case is said, imagine that instead of assigning values to, like on R, I had to assign values, say, on the first n integers. So like imagine I had like a function, let's say that instead I had a function, you have a function from the set of 1, 2 until n. So into the integers 1, 2 until n. So you have like the first n integers, and you have to send that to each of those first n integers have to be sent into one of the first n integers. So this is kind of like a combinatorics problem, right? How many ways can you do that? A function is just an assignment, right, of numbers. So the first any of these integers, right, we have n options where you can send it, right? So how many functions are there from these between these two sets? How many functions? Well, and again, you're thinking about this set as being S. So, well, again, like the number 1 can be sent to M options, the number 2 can be sent to N options, number 3 can be sent to N options, number N can be sent to N options. So each of them has M options. So M times N times N times N gives you M to the N, right? So, like all I'm saying is that f of S1, f of S1, so, or f of 1, right? Because I'm calling them f. In fact, if you can even call it, like maybe I'll call it S1, S2 up to Sn to kind of like be a bit more abstract. So f of S1 has options. F of S2 has options, and f of Sn has options. And again, it's kind of like the basic combinatorics principle that all the possible ways of assigning this is like m times m times n, right? So you end up with, you have m times n times n, times n, how many times? M to the n, right? But that is, that is, so it's kind of like an exponent notation, right? Like it's a power. So it's n to the cardinality. Sometimes like the number of elements of a set is called, well, I mean, it's always called like that. Like the number of elements of a set is called its cardinality. So if you notice here, like, it gives you n to the cardinality of that set. So that in the continuous case, when it's not that you have to send it to the final list of numbers, but it can be any number on the number line, kind of by analogy, you still call it R to the S, just because it kind of like, in an analogy with how you're writing this here. Is that okay? Is that making sense? Okay, that was enough of a detour for like all this notational stuff. Now let me give you an example of the type of things that we're going to be analyzing. So I'll kind of like introduce like the definitions next time. I just want to kind of like give you a quick example of like kind of like similar setup to the like what we will be studying moving forward. But so what I'm going to give you is what's called like a simplicial complex, which is a generalization of a graph. So that's a good way to think about it. So again, I'll give all the definitions like on Thursday, but so I'll tell you about a simplicial complex. And this is called a generalization of a graph. It's like generalization of a graph. So again, like graphs, I think is something everyone is kind of more or less acquainted with. Like, a graph has like certain nodes or vertices, right, which are connected with segments or like sometimes called like edges. But a simplicial complex is kind of like a generalization of that idea. So again, like, just to give something super, super concrete, let me show you what it could be like. So I'll call it. So again, if you just were calling this like from the perspective of like graph theory, like when you call these like four nodes, or like I'll call them vertices, because that's kind of going to be like our center name. So I'll label them some, like, I'll call them V1, V2, sorry, V0. It's convenient to start the labeling at zero. You'll see why next time. But like the elements, I'll just call V0, V1, V2, and V3. Okay, so you have four nodes or four vertices. So the letter V is just for vertex. And again, in a graph, you typically would connect those like using edges, right? It will be convenient, a bit arbitrary at the moment, but I'll draw these edges as being directed. And my convention for the direction of the edges will be that if I'm going to draw an edge, I will direct it so that it goes from the, in order of like, from the smaller index to the larger index. So for example, let's say that first let me draw the edges that I wanted to think about. Well, I have 1, 2, 3, 4, 5. I have 5 edges here, right? Those are not all the possible edges, right? There are tons that I could others that I could have drawn, right? For example, there's one from B1 to B3, like in principle, theoretically. So that's not an exhaustive list by any means, right? Like for example, here's like an idea of like how could you do this, like that's why graphs are useful, because it's just like a visual way of like representing like like information. So like you could draw if you thought about the vertices as people, you could draw an edge if they're friends or not, right? Like so if there's an edge, that means that the people represented by these vertices are friends. And if there's no edge, they're not friends or they don't know each other, however you want to interpret that. Okay. And then again, like for example, something like friendship has no see, we talked about that before, right? Like, you expect hopefully symmetric, right? So it's not, you're your friend, then I'm your friend, etc. But again, I'll just introduce an arbitrary orientation, that's the word for it, where I'll draw, kind of make it look more like an arrow, where I'll orient the arrow so that it goes from the smaller index to the larger index. So for example, in this case, if I, for this edge that connects V0 and V1, it goes from 0 to 1. And again, I'll kind of like introduce like all those conventions next time. But for now, I'll go from 0 to 1. Then the other one goes from 1 to 2, right? Um, and then, then from 0 to 2, there would be an edge, right? Because again, I'm always starting my arrows or my vectors, if you want to call them like that, with the going from the smaller index to the larger index. And then, okay, 2 is less than 3, so I will draw one from 2 to 3. And then, 0 is less than 3, so I will draw one from 0 to 3. Okay, so far so good. Then get to okay, so, and then like again, like this is more or less like where, like, I mean, of course, graphs can be very integral, but that's more or less what where graph theory ends, in the sense that a graph is just like vertices and edges, right? Like sometimes you orient them, which is what I just did, other times you don't, but that is essentially what a graph is like. But a simplicial complex, essentially, what it does is kind of like the way which generalizes a graph is that because you can kind of like, again, like if you think about this as connections between the people, sometimes there are relations between people which are not like pairwise but are triple wise. I think the word for it would be triple wise. So for example, like, another case would be like publishing a paper, or like or right, submitting an assignment, right? So you can submit an assignment in pairs, but you could also submit an assignment in triples of people, right? So I'll draw a triangle. If let's say B0, B1, B2, submitted an assignment where like the three were like authors of it. So I'll draw a triangle, I'll kind of like fill in this triangle, like triangle that you see here. So I'm adding kind of something of higher dimensionality, right? Because a solid triangle has kind of dimension two in a sense. Uh, so, and again, like, so like there are many circumstances like where this is like a very natural thing to do. We'll do many, like in a sense, it's just kind of we'll go over many such examples. Another thing is that you could just think about this as kind of like an actual like geometric space. So my geometric space is like, oh, I just happen to have a triangle, and for some reason, like, I added these two edges, right? So you can also just think about this as a geometric space. You don't have to think about it in this like uh relations or like the networks example that I was just giving you. But so there are multiple interpretations or how you could think about this. And again, you could orient the triangle, you could orient this triangle as well. And in physics, you have like this right hand rule or a left hand rule, like for oriented things, but for us as well in mathematics, like of whether you're moving clockwise or counterclockwise, right? So I'll kind of like add kind of like an indication that I'm going to travel along this triangle in a particular way. I don't know, I hope I did it in the way I'm thinking I did it. I don't know what I wrote all of this. Let me see what you did mention. Ah, here you are. I was wondering where I had drawn it. So I'll use the standard convention is to move counterclockwise, right? So like when you're reading angles and the unit circle and things like that. So I'll draw kind of like I'm sorry about that. I'll draw something like this, kind of like to kind of like indicate that somehow like the way I'm thinking about orienting the triangle will be in this counterclockwise way. So in terms of like structures, what do we have? I have, oh, by the way, I still haven't labeled things, so I'll call T the triangle. There's only one solid triangle in this picture, so I don't have to worry too much about being super fancy with the names. So I'll call this one T. And the edges, I'll kind of like refer to them in a clever way. So I'll just refer to them, you know, because this one goes from 0 to 1, I'll call this E01. Because this one goes from 1 to 2, I'll call this edge E1, 2. So I'll kind of like name the edges according to their like sometimes that's called, starting point, final point, or like their source and target, which is the other name for this. Okay, so far so good. Everyone will be up to this point. So if you think about it kind of like in terms of geometric data, what do we have? We have one triangle, one solid triangle. So we have one triangle, which I'm calling T. We have five. How many edges do we have? We do have 5 edges, right? We have 5 edges. Okay, so here is not oh, okay, so again, like I'm going to list them in a particular order, like the way you list them, which is the first one, the second, the third, like that is not that important. But like I'll just list the first 3 edges of this triangle and then I'll complete it with this other two. So okay, because like we're going to work in a moment, with the spaces of functions for each of these data, geometric information. So like I want to kind of like consider like a vector in R5, right? Because I got 5 edges. So I just want kind of like a standard way to list them. And then we end up with 4 vertices, right? So we have 4 vertices. Which, well, okay, those are kind of like ordered in the standard way, like just V0, V1, V2, V3. Okay. Okay, so far so good. Okay, now comes the fun part. So now in the context of what we have been working on like last week and maybe 2 weeks after, maybe we have these two matrices A and B, right? We have these two matrices A and B that multiply to 0. So I'm going to define them for you now. So the point of the matrices is that in a sense they kind of like give you the boundary of each of these geometric data. So for example, like maybe this is a little bit, the edges are a little bit easier to understand, right? What is the boundary of an edge? It's just like, the initial point and the final point, right? And because one is at the beginning and the other is the end, I'll subtract them. So like, it kind of like what's going to happen is that I'm going to have, I'm going to have 2 matrices here, but for that, again, we have kind of like 3 sets here. That's what I want you to think about it in this way. So just to use the set notation, I'll call, you have this set of a single triangle, a singleton, this set of 5 edges, and this set of 4 vertices. Okay? So I'm going to define, because of what we were talking about, because this has one element, the space of functions on that element is just R, right? So the space of functions, of like the triangle into the reals is just the vector space R, right? Like one dimensional. the space of edges. Let's call this set E for edges. The functions from the edges into the reals is just R5, right? And the space of vertices, right, like this set V. So the functions of the vertices into the reals, that would be R4, right? So I'm going to give you two matrices. One goes from the space of, the space of triangle of functions into R5, and the other one goes from this R5 into R4. So this is going to be the matrix that I called B before. I'm calling this one B. And this one is going to be A. So again, like just to kind of show you that it really does correspond to what we were having before. Sorry, just to go back to it for a second. If we look at the situation that we had before, right? We had three vector spaces. We had three vector spaces of different dimension in principle, and you have two matrices between those vector spaces, right? So that's kind of what I'm trying to go for at the moment with this. Okay. Okay. Now, here's something useful about like a matrix, because it's a linear transformation, right? If you want to define a matrix, you just have to define it on a basis. That's the beauty of a linear transformation. I mean, that's why it's useful to think of a matrix as a linear transformation. So to specify a matrix, I just have to tell you what I wanted to do on a basis for that vector space, and that determines completely the matrix. So to specify the matrices A and B, I just need to specify them on a basis for the vector spaces. So again, like, let me start with A, because A is a little bit more intuitive, even that you have more familiarity with graphs. So to specify the matrix A, I have to specify it on the basis vectors, right? But because of that, I was telling you about these formal linear combinations, thinking about specifying A on the basis is kind of like more or less equivalent to saying what I want A to do to this edge, what I want A to do to this edge, this edge, this edge, and this edge. Okay. So basically A has to be, so if you want to specify A, you have to specify A on the 5 edges. Let me move this a little bit. So again, the 5 edge, here you have to kind of corner them in some way. So my 5 edges are going to be these 3 and 5 that I have there. And again, this is why this is a useful notation, because again, like this is supposed to be the matrix takes like the basis vectors, and it has to produce something in R4. But what is something in R4? It's a linear combination of the basis of R4, but the basis of the R4 are kind of like the vertices. So you're allowed to map them to linear combinations of vertices. So for example, what should A map E0, 1, 2? It will map it just to the endpoints of that edge. So it will map it to vertex 1 minus vertex 0. So I'll map these two. Sorry, just to go back for a second, that's why I was saying a bit earlier that it was useful to think about the vector in terms of a sum, of the underlying set as a linear combination of the underlying set, because it kind of like makes it a bit more transparent what you're trying to do here when you define these formulas. Okay. So again, the minus there is just to reflect the fact that you think of this edge as going from vertex 0 to vertex 1. That's kind of like the point. And same goes with the others. So V2 minus V1, the other one is V2 minus V0, and the other one is V3 minus V0, the other one is V3 minus V2. That okay, so making sense so far, so good. Kind of like, oh, but let's think about this a bit more clearly. You know, you can think of this as being -1. Let me see it. You know, you can think about it as being, oh my God, this is, okay, let me put it like this. V0, V1, 2, V3. So give me a second. You'll see what I'm doing in a moment. And my God, with all these copy pastes, this will take up for an eternity. Okay, so okay, so here's another way of thinking about V1 minus V0. You can think about that as being minus V1 plus 1 V0 plus 0 V2 plus 0 V3. So kind of like write it down explicitly as a linear combination of the basis vectors. So this will be minus V0 plus 1 V1 plus 0 V2 plus 0 V3. Then the other one would be 0, okay, there's no, there's no V0, then there's minus V1 plus 1 V2 plus 0 V3, and you kind of like can see where I'm going with the others, right? Like, so you do minus V0 plus 0 V1 because there's no V1 plus 1 V2 plus 0 V3, right? And then then you get minus V0 plus 0 V1 plus 0 V2 plus 1 V3. And then you get 0 V0 plus 0 V1 minus 1 V2 plus 1 V3. Okay, so making sense. Kind of like, and why am I doing that? Because how many numbers do you get here? Like you get 4 for each equation, right? You get 4 times 5, 4 times 5. But this matrix A should be represented as a 4 by 5 matrix. So that is like these are the numbers that give rise to the matrix representation for A. Uh, which I don't know if that's something, I don't know, like you had done before, like in linear algebra, but one way, if you define a linear transformation, one way to find the matrix associated to it is that you expanded everything out in terms of the basis vectors and the coefficients are just like the entries of the matrix. Okay, this matrix A, because it goes from R5 to R4, this has to be a 4 by 5 matrix. Again, it's kind of this annoying thing where the number gets flipped. So I had to find somehow base 20 numbers, right? Like these 20 numbers are essentially these 20 coefficients from the linear combination. So it's just that it's kind of like becomes the first column, this is the second column, this is the third column, this is the fourth column, this is the fifth column. So you have to kind of the way I'm expressing it out, there's kind of like a transposition. So the matrix A, so you read off, so you rearrange these 20 numbers into a 4 by 5 matrix to obtain the matrix A. So again, those are like the same 20 numbers that you saw there, and just like, the numbers that appear in one equation becomes like the coefficients of the entries of that particular column. So for example, sorry, just to go here for a moment. If you look at the third equation would be -1, 0, 1, 0. So -1, 0, 1, 0 would be the entries in the third column. So if you go to the third column here, you'll see -1, 0, 1, 0. Okay, so that's how you build up the matrix A. And then the matrix B, what is the matrix B? So let me copy paste this picture because that way I can kind of explain it a bit more easily. So for the matrix B, oops. So again, so for the matrix B, is defined on the vector space. It goes from the vector space of functions of the triangle to the vector space of functions of the edges. So again, to define a matrix or a linear transformation, you just have to define it on a basis. Because it is one-dimensional, it only has a basis, a single basis vector, which is provided by this triangle. So you just have to define the matrix B on the triangle. Okay, so you have to define B on the triangle. So you have to tell me what B of T has to be. Okay. And again, if you read, and that's where like this counterclockwise notation is useful, because if you read this, then you can check, oh, as I move counterclockwise, does that agree or not with the edges? So for example, if you're moving counterclockwise, you have E01 plus E12, but then you're going against E02. So this would give you E01 plus E12 minus E02. Is that making sense? Again, because you have to imagine you're moving counterclockwise along the triangle. So if you move counterclockwise, you're moving in the same direction as E01. You're moving in the same direction as E12, but then you're going against E02. That's why there's a minus there. And one way to write this is that this is the same as saying that this is what, like E01, E12, E02, E03, E23. So this would be 1, E01 plus 1, E12 minus 1, E02 plus 0, E03 plus 0, E23. Right? That's explicitly as a combination. And what is this matrix supposed to be? This matrix should be a 5x1 matrix. A 5x1 matrix is just a vector in R5. So what are the answers of these vectors? One, like these coefficients. Okay, I'm almost done here. So the matrix representation of this linear transformation is just like these 5 numbers: 1, 1, -1, 0, 0. That makes sense. How I treat the matrices. And kind of like, I mean, I still haven't said, I'm not going to explain today why that happens because like we're almost run out of time. But at least in a calculation, I just gave you two matrices, you can multiply them. And the fun thing is like, oh, if you multiply them, you do get the zero matrix. Oh, that's kind of fun. Okay, so it's like a fun check if you want. Just check that if you do A times B, right? So let's just kind of like, let me copy paste the matrices. So if you got A, again, I still haven't given like a good geometric reason for what that would happen, but if you do A, or how is it? I think that's how I wrote it, right? Like A times B, that should be. because A is like a 4 by 5, yeah, A is 4 by 5, right? And B is like 5 by 1, so this is fine. And B was 1, 1, -1, 0, 0. So yeah, these two matrices can be multiplied for sure, right? You would end up getting like, you know, you would end up getting a 4 by 1. Oh, you get like the vector, right? Like, so you end up getting a 4 by 1 matrix, which is just like a vector. But kind of like a fun check if you want to do it. Although this will always happen because of like the way we're defining it, is that you get 0, 0, 0, 0. Okay, so because of that, you can kind of like run the thing that we were talking about. You can do this quotient vector space, etc., etc., and that ends up taking you to considering this Laplacian matrix. I'm not going to write more today of what this is. I'll kind of like finish this next time. But once once you know that you are in this setup, you would be interested in finding this Laplace matrix. And we'll see this next time, but the nullity, this null space of L will have dimension 1, has dimension 1. Okay, so the question would be, oh, what does it mean that the null space has dimension 1? What it means in this particular case of the graph, not the graph, the simplicial complex, is that if you thought about it as a geometric thing, it kind of like has a hole here because I didn't fill out this other region with a solid triangle. So there's a hole, there is a hole there, and this nullity somehow is kind of like computing the fact that there's like a hole there. So kind of like these dimensions of the vector spaces, we will kind of like tell you kind of like in a sense like the number of holes that the space has. And again, like you have to develop some intuition to convince yourself that that kind of like works nicely. But again, it will have important applications. And we'll start talking about this like in some future classes. But in the next time, I'll kind of put things a bit more concretely, and we work out some other examples of this sort. But we're already starting to get to kind of like the meat of the course, which is like computing these matrices and these like Laplacian matrices and all this stuff. So let's finish here, and then on Thursday I'll keep telling you more about. I'll make just this here.